These are the answers to the AP Chemistry packet on topics 3.3 to 3.6. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. Question 1 says, based on the information in the table above, which of the following particulate diagrams is the best representation of an equimolar mixture of fluorine, F2, and iodine, I2, at a temperature of 200 kelvins? Now, the content from the AP Chemistry course and exam description that is the most relevant to question 1 falls under topic 3.3, solids, liquids, and gases. And the two essential knowledge statements that are highlighted on this slide are: the solid and liquid phases for a particular substance typically have similar molar volume because in both phases the constituent particles are in close contact at all times. In the gas phase, the particles are in constant motion, their frequencies of collision and the average spacing between them are dependent on temperature, pressure, and volume. Because of this constant motion and minimal effects of forces between particles, a gas has neither a definite volume nor a definite shape. So the message from those two essential knowledge statements can be represented on this slide, that in general, particles in the solid phase and the liquid phase tend to be rather close together, whereas particles in the gas phase tend to be rather far apart. So we know we have a mixture of fluorine and iodine, and in these particulate diagrams we can see that one form of matter is in the solid form where the particles are close together, and then another form of matter where the particles are farther apart would represent a gas. Now, it does say, both in the question as well as in the table, that the formula for fluorine and iodine is written with a subscript of 2. So these are diatomic elements, and so fluorine and iodine exist in the form of diatomic molecules, so we can eliminate choices A and B, because if you look at the particles in the top portion of those particulate diagrams in choices A and B, those particles are represented as individual atoms instead of diatomic molecules. So we know the correct answer that features diatomic molecules would be either C or D. Let's take a closer look at the melting point and the boiling point of each substance and compare those numbers with a temperature of 200 kelvins. Now, at a temperature of 200 kelvins, which is greater than the boiling point of fluorine, that would mean that at 200 kelvins, fluorine, F2, would exist in the form of a gas. And since 200 kelvins is less than the melting point of iodine at 387, that means that at 200 kelvins, iodine would exist in the form of a solid. So the correct particulate diagram should show solid iodine and gaseous fluorine. So the correct answer to question 1 is choice C, which shows solid iodine and gaseous fluorine. Now let's take a look at question 2. Question 2 says, based on the information in the table above, which two gas samples contain the same number of moles of helium gas? Let's take a look at the AP Chemistry equations and constants sheet. In this section, which is entitled Gases, Liquids, and Solutions, you can see the ideal gas law, PV equals nRT, where the variables P, V, T, and N stand for pressure, volume, temperature, and number of moles. You can also see two commonly used values for the ideal gas constant R, which have units of pressure of either atmospheres or torr, and the volume is in liters, the number of moles is obviously in units of moles, and then the temperature is in units of kelvins. Now, normally when I do calculations involving the ideal gas law, I pay close attention to my units to be very careful that I make sure I have the right units for pressure, volume, temperature, and number of moles. But in question number 2, I don't actually need to calculate the number of moles. I just need to set up an expression using the ideal gas law, so PV equals nRT. I'm going to calculate the number of moles by solving for N in that equation, so N equals PV over RT. So as long as I can find 2 of the samples in this table that have the same mathematical expression for PV over RT, that will be my correct answer to question 2. So I'm not actually going to use units when I set up these mathematical expressions, and I'm not actually going to solve for the number of moles. I'm just simply going to compare the ratio of PV over RT for all 4 samples, and whichever 2 samples gives me an identical mathematical expression, then that must be the correct answer. So let's go ahead and start with sample number 1. Now the volume and the pressure would be on top, so P times V, that would be 3 times 2. And on the bottom, it's R times T, that would be R times the temperature in Kelvin, 200. Now 6 over 200 is the same as 3 over 100, so on my calculator, I would get 0.030 over R. Again, this is not the actual number of moles, but simply a mathematical expression. Let's move on to sample 2. So pressure times volume would be 2 times 3 on the top, and on the bottom it's R times T, so R times 250. Now 6 divided by 250 gives me a value of 0.024 on my calculator. So 0.024 over R, that's a different mathematical expression, so I already know that I can eliminate choice A, because samples 1 and 2 do not give me the same mathematical expression. Moving on to sample 3. We have a pressure of 2. We have a volume of 4.5, so 2 times 4.5 on the top. And on the bottom, we have R times T, where the temperature is 300 kelvins. So 2 times 4.5 is 9. 9 divided by 300 on my calculator gives me a value of 0.030. So now I can see that mathematically, the expression for sample 1 and the expression for sample 3, that PV over RT expression, is mathematically the same. So I'm pretty confident that the correct answer to question 2 is choice B, because samples 1 and 3 gave me the same value for that ratio of PV over RT. But just to make sure, I'll go ahead and process the data for sample 4. So pressure times volume would be 4 times 6, and then divided by RT, where the temperature is 500 kelvins, and on my calculator, 4 times 6 is 24, and 24 divided by 500 gives me a value of 0.048. So now take a look at those expressions that I've just calculated for the ratio PV over RT. Again, the correct answer to question 2 is choice B, because when I plug in the numbers from the table for that expression for the number of moles, PV over RT, samples 1 and 3 give me identical mathematical expressions. Now let's take a look at question 3. Question 3 says, based on the information in the diagram above, which of the following choices correctly compares the pressure of argon with the pressure of helium and provides the correct justification? Assume that both gases are at the same temperature and behave ideally. So in the diagram, we have helium in the flask on the left, and we have argon in the flask on the right. So I'll start with the flask on the left that contains helium. There are 20 grams of helium. And based on the information on the periodic table, the molar mass of helium would be 4 grams per mole. And so 20 grams of helium divided by the molar mass of 4, that tells me that there are 5 moles of helium in that flask on the left. Now I'll do a similar calculation to figure out how many moles of argon are in the flask on the right. So we have 400 grams of argon, and based on the information on the periodic table, the molar mass of argon, because it's 39.95, that's very close. I'm going to round that up to 40. So 400 grams of argon divided by the molar mass of 40, that tells me that there are 10 moles of argon in that flask on the right. So each flask contains a different number of moles of gas. We have 5 moles of helium and 10 moles of argon. Here is the ideal gas law, so PV equals nRT. And since I'm trying to compare the pressure of argon with the pressure of helium, let me go ahead and set up an expression using the ideal gas law to calculate pressure. So rearranging the ideal gas law to solve for pressure, that would be P equals nRT over V. Now the number of moles of helium, I just calculated that, that's 5 moles. So 5 moles, they're at the same temperature, but I don't know what that temperature is. So right now I have 5 times R times a temperature, which I don't know what that is, divided by volume, and it says in the diagram the volume of the flask on the left is 10 liters. So right now I have an expression which is 5 times R times T over 10. Let me do a similar calculation for the sample of argon. So P equals N R T over V, where the N, the number of moles, would be 10 moles of argon times R times the temperature, which I don't know what that value is. I just know that the temperature is the same for each gas, and then divided by the total volume. And you can see that in the diagram it says that the volume of the argon container in that flask on the right is 20 liters. So let's compare the two mathematical expressions for P equals nRT over V, which would give me the pressure of each of these gas samples. So 5RT over 10, 10RT over 20. Hopefully you can see that 5 over 10 is equal to 10 over 20. So what that tells me is that these two gases have the exact same pressure. And so now look at the 4 choices, A, B, C, and D. Choices A and B say the pressure of argon is less than 12 atmospheres. I know that's not true, so I'm going to go ahead and eliminate choices A and B. I know that the pressure of argon is the same as the pressure of helium because 5RT over 10 is mathematically equivalent to 10RT over 20. But now what I have to do is focus a little bit more on the difference between choice C and D. Let's take a look at that justification in choice C. It says if two gases are at the same temperature, they will have the same values for both pressure and average kinetic energy. So this reminds me of topic 3.5 in the AP Chemistry course and exam description. So this essential knowledge statement that is highlighted on this slide says, the Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles in that sample. So that tells me that if I have two gases at the same temperature, then they have the same kinetic energy. But that's it. It says nothing about the pressure. So yes, these two gases would have the same temperature and the same average kinetic energy, but I can't assume that they would necessarily be at the same pressure. Just because they're at the same temperature, that's not a guarantee that that means they have to have the same pressure. Let's take a look at choice D in terms of the justification. It says compared to the helium sample, the argon sample contains twice as many gas particles. Well, that's true. We have 5 moles of helium. We have 10 moles of argon, so that's true. And occupies a volume that is also twice as much. That's also true. We have 10 liters for the sample of helium, and we have 20 liters for the sample of argon. So look at that mathematical ratio. Because 5RT over 10 is mathematically equivalent to 10RT over 20, that tells me that the reason why these two gases have the same pressure is because we have doubled both the number of moles and the volume, and that keeps that ratio the same. So the correct answer to question 3 is choice D. Now let's take a look at question 4. Question 4 says the table below contains information about samples of 3 different gases. Each gas sample occupies the same volume and is at the same temperature. Which of the following is the most likely identity of the gas in container 3? Assume that all three gases behave ideally. So what I'm going to do is focus on the four variables that describe a gas, and they are volume, temperature, number of moles, and pressure. Now, we are already told in this problem that each gas sample occupies the same volume and is at the same temperature, so the other two variables, the number of moles and the pressure, those are going to be important for us to analyze to figure out the answer to question 4. So I'll start with number of moles. Each of these gas samples has a mass of 4 grams. So using the information on the periodic table, the molar mass of helium is 4 grams per mole. So if we have 4 grams of helium, we have 1 mole of helium in container 1. Now the molar mass of oxygen, O2, is 32 grams per mole. And so if I have 4 grams of oxygen, O2, 4 divided by 32 gives me 0.125 moles of oxygen. Let's look at the ratio of moles. The moles of helium is 1. The moles of oxygen, O2, is 0.125. That is an 8-to-1 ratio. So if you pick up your calculator and you do 1 divided by 0.125, you get an 8-to-1 ratio in terms of moles of helium to moles of oxygen. Now take a closer look at the pressure values from the information in the data table. The ratio of pressure of helium to pressure of oxygen is also in an 8-to-1 ratio. So what this illustrates are important relationships between gas variables. So the conditions in this problem are same volume and same temperature. So when you have constant volume and temperature, then the pressure is directly proportional to the number of moles. So that means if I have 8 times as much in terms of moles, then the pressure will be 8 times as much as well. So now I'm going to compare container 2 and container 3. So container 2 contains oxygen. Container 3 has the unknown gas that we haven't identified yet. I'm going to focus on the pressure ratio. And you can see from the information in the data table that the pressure of the unknown gas is twice as much as the pressure of the oxygen. So based on that information that I was just talking about in terms of the pressure is directly proportional to number of moles, since the pressure ratio is 2-to-1, then that means that the mole ratio will also be in a 2-to-1 ratio as well. So my conclusion is that container 3, which contains the mystery gas, has twice as many moles of gas as container 2, because the gas pressure in container 3 is twice as much as it is in container 2 under these conditions of constant volume and temperature. Well, now that I know that the mystery gas in container 3 has twice as many moles of gas as container 2, let's compare the number of moles of oxygen with the number of moles of the mystery gas. So we've already determined that the number of moles of oxygen is 0.125 because 4 divided by 32 is 0.125. Now we have 4 grams of the mystery gas, and since I don't yet know the molar mass of the mystery gas, but I do know it should contain twice as many moles, 0.125 moles times 2 gives me a value of 0.250 moles. So 4 grams divided by what number will give me a value of 0.25? Well, 0.25 is 1/4, and 4 divided by 16 is 1/4, or 0.25. So the molar mass of the mystery gas is 16 grams per mole. And now that I know this information, that the molar mass of the gas in container 3 is 16 grams per mole, all I have to do to answer question 4 is simply look at the chemical formulas that were given for choices A, B, C, and D, and then use the information on the periodic table. So the correct answer to question 4 is choice B. So CH4, which is called methane gas, has a molar mass that is approximately 16 grams per mole. So carbon is 12. The atomic mass of hydrogen is approximately 1. So 12 plus 1 times 4 is 16. And then just to show you the molar masses of the other gases for choices A, C, and D, the molar mass of hydrogen H2 is approximately 2 grams per mole. The molar mass of neon is approximately 20 grams per mole. And the molar mass of SO2, or sulfur dioxide, is approximately 64 grams per mole. So based on this information in our calculations, the correct answer for the identity of the gas in container 3 is CH4, because it has a molar mass of 16 grams per mole. Now let's take a look at question 5. Question 5 says, based on the information in the table above, which of the following choices correctly identifies the sample that has a greater density in grams per liter and provides the correct justification? Assume that both gases behave ideally. So the 4 variables that are normally used to describe the properties of a gas are volume, temperature, pressure, and number of moles. So examining the information in this data table, we can see that each of these gas samples has the same volume and the same temperature. That means that we can focus our attention on the ratio of pressure and moles. So like I had mentioned in question 4, under conditions of constant volume and temperature, the pressure of the gas is directly proportional to the number of moles of gas. Now what I can see in this data table is that the pressure of the CH4 sample is 4 atmospheres, and the pressure of the C2H6 sample is 2 atmospheres. Remember, the gas pressure is proportional to the number of moles of gas under these conditions of constant volume and temperature. So I can conclude, based on this pressure information, that the CH4 sample has twice as many moles of gas as the C2H6 sample. And the reason why is because the gas pressure of the CH4 sample is twice as much as the gas pressure of the C2H6 sample. So again, under conditions of constant volume and temperature, pressure and moles are directly proportional. Now, we don't know the exact mass of each gas. That was not given explicitly in this data table. But we do know the identity of each gas, and we are given the molar mass. So the molar mass of CH4 is 16 grams per mole, and the molar mass of C2H6 is 30 grams per mole. And we've already determined, based on that pressure ratio, that the number of moles of CH4 is twice as much as the number of moles of C2H6. So 2 moles of CH4 would have a total mass of 32 grams. 1 mole of C2H6 has a total mass of 30 grams. So now we have enough information to say with confidence that the mass of the CH4 sample is greater than the mass of the C2H6 sample. And since these 2 gas samples have the same volume, that means that the density of CH4 will be greater than the density of C2H6, because density is mass divided by volume. So the correct answer to question 5 is choice A. The sample that has a greater density is CH4, and the justification is because the mass of the CH4 sample is greater than the mass of the C2H6 sample. Now let's take a look at question 6. Question 6 says the figure above represents 3 sealed 2.0 liter vessels, each containing a different inert gas at 298 kelvins. The pressure of argon in the first vessel is 1.5 atmospheres. The ratio of the numbers of argon, neon, and helium atoms in the vessels is 1 to 2 to 3, respectively. So if we count the particles in each container, I see 2 particles of argon in the first container, and I see 4 particles of neon in the second container. That is a 2 to 1 ratio between neon and argon. So if I want to figure out the pressure of neon, I know that the volume is not changing, the temperature is not changing, so the pressure of neon should be twice as much as the pressure of argon because there are twice as many neon particles compared to argon. So 1.5 times 2, that would give me a pressure of 3 atmospheres for neon. Now, if I compare the first container, which is argon, and then that third container of helium, I can see that that ratio of particles is a 1 to 3 ratio. So there's 2 particles of argon in the first box, and there's 6 particles of helium in that third box. So with that 3 to 1 ratio, again, we're not changing volume, we're not changing temperature, I can say that 3 times as many particles means 3 times as much in terms of the pressure value. So 1.5 times 3 is 4.5 atmospheres. Now, we're not quite done in answering this question, but we have now determined, based on the information in the diagram, the pressure of each gas. So it says after all of the gases are combined in a previously evacuated 1.0 liter vessel, what is the total pressure of the gases at 298 kelvins? So what I'm going to do is make an assumption. This will not get me to the correct answer right away, but it will help me process mathematically what's going on with this gas mixture. So the assumption that I'm going to make for just the moment is that we're combining all 3 of these gases into a 2-liter container. Again, this will not give me the final answer, but it's going to be easier for me to process. Take a look on the equation sheet. You have a mixture of gases, and on the equation sheet, there is an equation for total pressure. It says the total pressure of a gas mixture is equal to the sum of the individual partial pressures of the gases in that mixture. So if I was combining 1.5 atmospheres of argon, 3.0 atmospheres of neon, and 4.5 atmospheres of helium in the exact same size container, so not changing the volume of the container at all, then I could simply add each of these partial pressures together. So 1.5 plus 3 plus 4.5 would give me a total pressure of 9 atmospheres if the mixture occupies a 2-liter vessel. So 9 atmospheres is not the correct answer to this question, but at least it helps me process what the mixture's total pressure would be if we did not change the volume of the container at all. But in fact, we are going to change the volume right now. So it's not a 2-liter vessel, it's a 1-liter vessel. So think about the relationship between pressure and volume. And so to help you, I'll put that slide up that I had showed earlier in this video. Earlier, I was talking about under conditions of constant volume and temperature. I said that pressure is directly proportional to number of moles. But take a look at that first relationship. Under conditions of constant number of moles and temperature, pressure is not directly, but rather inversely proportional to volume. So what does that mean when I say inversely proportional? That means as one variable increases, the other variable will decrease by a proportional amount. So we take the same number of moles of gas, but we put it into a container that has exactly half the volume. And so when you cut the total volume of the gas mixture by half, you will double the pressure. So P times V equals P times V. If I have a pressure of 9 atmospheres in a volume of 2 liters, then when I reduce that volume to 1 liter, the pressure will double to 18 atmospheres. Now that number, that is the correct answer to question 6. So what I first did was figure out the pressure of each gas. Then I assumed that the total volume of the gas mixture was the same as what I had been combining in the first place. But once I decrease the volume of that gas mixture by a factor of 2, then I have to increase the total pressure by a factor of 2. So again, the correct answer to question 6 is choice D, 18 atmospheres. Now let's take a look at question 7. Question 7 says the reaction between nitrogen monoxide, which is NO, and oxygen gas, which is O2, to produce nitrogen dioxide, which is NO2, in a rigid reaction vessel, is represented in the diagram above. The pressure inside the container is recorded using a pressure gauge. Which of the following statements correctly predicts the change in pressure as the reaction goes to completion at constant temperature and provides the correct explanation? Remember, the four variables that we typically use to describe the properties of a gas are pressure, volume, temperature, and number of moles of gas. Now, two of these four variables are not changing during the course of this experiment. So, which two variables are not changing? Well, it does say in this question that the reaction goes to completion at constant temperature. So temperature is not changing. And it also mentions that this reaction takes place in a rigid reaction vessel. That means that the volume is not changing. So volume is not changing, temperature is not changing. So it comes down to pressure and number of moles of gas. And as I've mentioned a few times in this video, under conditions of constant volume and temperature, pressure is directly proportional to the number of moles. So let's focus our attention on the number of moles. Let's see how the number of moles or the number of molecules of gas changes during the course of this reaction. So the gas pressure is proportional to the number of moles of gas, and we start with a mixture of nitrogen monoxide, which is NO, and oxygen, O2. And then as the reaction comes to a completion, the only substance in the reaction vessel at the end of the reaction is nitrogen dioxide, or NO2. Now, this is an unbalanced chemical equation that I just wrote, so let me go ahead and stick in some coefficients into that unbalanced equation. So from left to right, when this equation is balanced, the coefficients will be 2, 1, and 2. So now that's a balanced equation. So I see a total of 3 moles of reactant particles, and I see a total of 2 moles of product particles. Or instead of just looking at the coefficients in the balanced equation, I could simply count the particles that are displayed in these particle diagrams. So there are 12 molecules of reactants, but there's only 8 molecules of product. So if the number of moles or if the number of molecules of gas is decreasing throughout the course of this experiment, then the pressure will decrease as well. So the total number of moles of gas in the container decreases, and this causes the total gas pressure to decrease. So as far as the 4 choices, A, B, C, and D, choice B and C talk about the pressure decreasing, but it's not about the average speed of the reactant particles in choice B. It is simply that there are fewer number of moles or fewer molecules of product in that container than there were reactants at the beginning. So number of moles decreases, which causes the total gas pressure to decrease as well. So correct answer to question 7 is choice C. Now let's take a look at question 8. Question 8 says the distribution of speeds of hydrogen molecules at 273 kelvins and 1 atmosphere is shown in the diagram above. Which of the following best shows the speed distribution of helium atoms under the same conditions of temperature and pressure? So the information for question 8 falls under topic 3.5, kinetic molecular theory. So here are the essential knowledge statements from the AP Chemistry course and exam description about the KMT. So the kinetic molecular theory, or the KMT, relates the macroscopic properties of gases to the motions of the particles in the gas. The Maxwell-Boltzmann distribution describes the distribution of the kinetic energies of particles at a given temperature. All the particles in a sample of matter are in continuous random motion. The average kinetic energy of a particle is related to its average velocity by the equation kinetic energy equals 1/2 mv squared, where m stands for mass and v stands for velocity. The Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles in the sample. And the Maxwell-Boltzmann distribution provides a graphical representation of the energies or velocities of the particles at a given temperature. So here on the equation sheet, you can see the kinetic energy equals 1/2 mv squared, where m is mass and v is velocity. Now, what you can see on this slide is something that I had presented in one of my earlier videos when I was talking about topic 3.5. Take a look at the relationship between the mass of the gas particles and the average speed. So if the gas particles have a smaller mass, then they'll be traveling at a faster average speed. And if the gas particles have a larger mass, then they'll be traveling at a slower average speed. So if you have two different gas samples at the same temperature, the gas with the smaller molar mass contains particles traveling at a faster average speed, and the gas with the larger molar mass contains particles traveling at a slower average speed. This can be visually explained with this Desmos activity, and there's the link at the top of this slide to where you can go play around with these variables yourself. So take a look. So now what I'm going to do is to increase the molar mass of the gas. And you can see that when I do that, the average speed of the particles decreases, so they're moving more slowly. Now I'm going to go in the other direction. So now the molar mass of the particles is getting less and less, and now the particles have a faster average speed. So if we look on the periodic table and compare the molar mass of hydrogen, H2, with the molar mass of helium, we discover that the molar mass of H2 would be 2 grams per mole, and the molar mass of helium is 4 grams per mole. So for hydrogen, those particles are going to be traveling at a faster average speed because there's less mass. And for helium, those particles are traveling at a slower average speed because there's more mass. And so which curve shows the dashed line traveling at a slower average speed? The correct answer to question 8 is choice A, showing that helium particles are slower and hydrogen particles are faster. Now, let's take a look at question 9, which is very similar to question 8. Question 9 says, the graph above shows the speed distribution of molecules in a sample of gas at a certain temperature. Which of the following graphs shows the speed distribution of the same molecules at a lower temperature as a dashed curve? So in question 8, we were comparing two different gases where the mass of the particles were different, but the temperature remained constant. So now in question 9, we're not focusing on the mass of the particles, but rather what effect does decreasing the temperature have on the speed. So let's go ahead and take a look at that Desmos curve one more time, but this time I'm going to change the temperature so we can see how that curve is affected. So now watch what happens when I decrease the temperature of the gas sample. You can see the average speed of the particles decreases. They start moving more slowly. If I increase the temperature of the gas sample, then the speed increases. So lowering the temperature causes the particles to move more slowly. So the correct answer to question 9, which shows the speed distribution of the molecules at a lower temperature, traveling at a slower speed, would be choice C. Again, lower temperature, slower average speed compared to the original gas. So correct answer to question 9 is choice C. Now let's take a look at question 10. Question 10 says, the experimental data in the table above indicates that NH3 gas shows a greater deviation from ideal gas behavior than CH4 gas does. Which of the following best explains this observation? So if you focus on those last two columns of the data table, you can see that the pressure calculated from the ideal gas law is supposed to be 2.84 atmospheres for each of these gases. But the observed gas pressure for CH4 is 2.82, which is slightly less than 2.84, and the observed gas pressure for NH3 is 2.78, which is also slightly less than 2.84. So the observed gas pressure is less than the pressure calculated from the ideal gas law. So this falls under topic 3.6 in the AP Chemistry course and exam description. This is deviation from ideal gas law. And so when I had taught this topic in an earlier video for topic 3.6, this is how I explained the situation. So the ideal gas law does not explain the actual behavior of real gases. Deviations from the ideal gas law may result from interparticle attractions among gas molecules, but they can also result from particle volumes, particularly at extremely high pressures. And so what I'm looking for is, why is the observed gas pressure less than the pressure calculated from the ideal gas law? And so here on this slide, this is what I had presented in an earlier video for topic 3.6. The effect of interparticle attractions on the observed gas pressure. In an ideal gas, it is assumed that there are no attractive forces between the gas particles. However, the particles of a real gas do experience attractive forces. This effect is especially noticeable when the gas temperature is relatively low, especially near the point at which the gas condenses to a liquid. Now, the attractive forces between the gas particles can decrease the force with which the particles collide with the container walls, as shown in the diagram above. This causes the observed pressure of a real gas to be less than the value predicted by the ideal gas law. So the fundamental explanation for why the observed pressure is slightly less than the pressure predicted by the ideal gas law is attractive forces between gas particles. Now let's go back and take a look at question 10. Each of these gases shows a slight decrease in the observed pressure compared to the ideal gas pressure. But we have to focus on, why does NH3 show a greater deviation from ideal gas behavior than CH4? Well, if it's about the attractive forces between the gas particles, then that's the explanation that I'm looking for. And so the correct answer is choice D. The attractive forces between NH3 molecules are stronger than the attractive forces between CH4 molecules. And you might already know that NH3 can participate in hydrogen bonding attractive forces, whereas CH4, which is nonpolar, can only experience London dispersion forces. So again, a greater attractive force between the NH3 molecules causes a greater deviation from the ideal gas law. So correct answer to question 10 is choice D. Now let's take a look at question 11. Question 11 says the experimental data in the table above indicates that the observed pressure of argon gas is greater than the pressure calculated using the ideal gas law. Which of the following best explains this observation? So we can see from the information in the data table that a pressure of 142 atmospheres is the pressure calculated from the ideal gas law for this gas sample. But the observed gas pressure is not 142, it's actually 145. So this is similar to question 10 in that it involves a deviation from ideal gas law behavior, but it's a deviation in the opposite direction. So in question 10, the observed gas pressure was less than the pressure calculated from the ideal gas law. And here in question 11, the observed gas pressure is actually greater than the pressure calculated from the ideal gas law. So we can already rule out choice C as a possible answer. And the reason why we can rule out choice C is because if attractive forces between the argon atoms, if that was going on, that would cause the pressure to be less than the ideal gas law value. So since the pressure observed for argon is actually greater, we know it's not about attractive forces between particles. So there must be another explanation. So in topic 3.6, which is deviation from ideal gas law, there are two explanations. There's interparticle attractions, which would explain why the observed pressure is less than the ideal gas pressure. Then there's also particle volumes. Let's take a look at the particle volume explanation. So again, this was information that I had presented in an earlier video for topic 3.6, deviation from ideal gas law. The effect of particle volume on the observed gas pressure. In an ideal gas, it is assumed that the volume occupied by the gas particles themselves is zero or negligible. The free space in which the gas particles can move around is equal to the entire volume of the container. However, the particles of a real gas do have volume and they do occupy space inside the container, and this effect is especially noticeable when the gas pressure is very high. Now, when the volume of the gas particles themselves becomes a significant fraction of the container volume, the free space in which the gas particles can move around is decreased, and this causes the observed pressure of a real gas to be greater than the value predicted by the ideal gas law. So the fundamental explanation here for why is the observed pressure greater than that of the ideal gas law, it's because the volume of the gas particles becomes a significant fraction of the container volume. So that's the explanation that we're looking for that would explain why is the observed pressure of argon gas greater than the value predicted by the ideal gas law. So the correct answer to question 11 is choice D. The combined volume of the argon atoms is too large to be negligible compared with the total volume of the container. So the correct answer to question 11, which has to do with particle volumes, is choice D. So question 11 is the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.